Okay, so let me start a new video. We were talking about tensile strength. One more thing about tensile strength is that the value of tensile strength is going to be given by this equation. Of course, the higher the force that the rock can resist, the higher the tensile strength of the rock is going to be. And in order to calculate tensile strength, you measure the maximum value divided by pi, L, and R, where R is the radius of the rock and L is the length of the rock in this direction from the bottom to the top. Here it will be perpendicular to the board, and then you get the value of the strength. Notice that basically is L times R times pi is more or less the area perpendicular to this direction. So force divided by area, that will give you the tensile strength of the rock. And here you have one example, and here you have typical strengths of different rocks. Let's see. For example, you can see that the tensile strength of rocks is in the order of 5 megapascals or less. How much is 1 megapascal? Do you guys remember? 1 megapascal is more or less in PSI. 145, right? Let's say 150. So 5 MPa, that should be what? 750, right? So 750 PSI. So if you had, like similar to this rock, a 1 inch square, this is less than 1 inch square, and you could hang 750 pounds from the rock. So that's to give you an idea of the tensile strength. It looks like a lot, but actually it is not. Compared to other materials like steel, in which you see the number over there, the tensile strength of steel is 500 times more. And the tensile strength of titanium is about 400 times more. So the tensile strength of rock is not a lot, actually. What would be the tensile strength of an unconsolidated sand or an uncemented sand? Zero, no strength at all. And we do find those materials in many of our applications. So many of those materials also are going to have a tensile strength which is equal to 0. They always have to be in compression. If they are not in compression, they can fail. And there is another example too that I have here in my box. So I told you, you can see, for example, typical sandstone, let's say 5 MPa, 750 PSI. In order to break it in tension, you'll need 750 pounds, more or less, for a 1 inch square. So I have an example here. And let me switch to the dock camera. Okay, so let's say I have a rock and I'm going to try to make it to fail in tension with my bare fingers. Do you think I can do that? No. Raise your hand if you think I can do that. One. I have one person, one supporter, two supporters. I'm very strong, I can tell you. I go do rock climbing and climb hard routes if I'm fit. And now I'm fit. I've been training for quite a bit. So no takers, another. I have two people supporting me. I can break it with my bare fingers. Okay, 3. All right. So look. I broke it. It seems like a silly example, but it's not. my point here is that tensile strength, especially, is a property that depends on direction. For example, if I try to now pull this with my hands, I'm not going to break it. It's too strong. But in this direction, I can break it. Similar to elastic properties, failure properties also can be anisotropic and depend on direction. And not only on direction, but also on scale. For example, I take just 1/2, and now I cannot break it in any direction. But if I were to take a bigger sample, like this one, I could take it. And this is very important because sometimes in many applications, we measure properties in small pieces of rock, like the ones I just showed before, and the application may not be that small piece of rock. You're drilling through a fractured rock. If your wellbore happens to land in the middle of the rock, where the properties of the rock are the properties of the rock matrix or the unfractured rock, then you will be fine considering the properties that you measure in the laboratory with a little sample that probably was this size. But if your wellbore happens to go through a place where there are already fractures, then the property of this entire medium is not the property of this small thing anymore. It's the property of the fractured rock. So tensile strength, although we're going to measure in the laboratory, you should be very cautious because at larger scales, it tends to be very anisotropic, and many times it's also going to be 0, especially when you have a fractured rock. And most fractures, most rocks, at some point, are fractured. And that's a point that I wanted to make with what we were discussing before about the scale of the process. It's not the same to deal with a problem that involves rock failure in a very small size, like for example, cutting rock you're drilling. When you cut the rock, the process zone, it's less than 1 inch. It's very small. Probably there you're engaging the full strength of the rock. You can go bigger, like at the size of the wellbore, but that still is relatively small. You can go a lot bigger when you do a hydraulic fracturing treatment, and here this can be hundreds of feet. This can be even close to a mile. And when you engage such a large process on, the properties of the rock are not going to be the same than the ones that we measure in a small thing in the laboratory. And sometimes you can go a lot bigger, like for example with reservoir depletion. And this is the example that we were talking about before in Long Beach. If you have a reservoir which is several miles long or even more, and you deplete it, the properties of that engage a mass of rock which is thousands or even more times bigger than a small piece of rock. So you have to remember that, okay? All right, so tension, that's mostly everything I wanted to say. And here you will find a few more things. You will do the laboratory on Friday with me here. And there's not a lot more to say about tensile strength. Any question about tensile strength? We're going to use it later on when we deal with problems of fractures in wellbores. Okay, so let's talk about the next one. And you know, I arrived a little bit late because I was trying to make an experiment work here in class, and it didn't work. So I'll try to have that by Friday. Hopefully it will work by then. I just have to fix a leak. All right, tensile strength done. The next thing that we're going to see is very important, and is shear strength. In tensile strength, remember that if, let's say, we have a piece of rock, we're pulling in a direction, and a fracture is being caused perpendicular to the direction in which we are pulling. Okay, shear strength is going to be different, and it's going to involve a shear between surfaces. Before we get to there, let me remind you something that you know very well, but it is the basis of shear strength. And this is the idea of friction. If you have a solid and you apply a normal force on top, what is going to be the force in perpendicular direction required to move that object? You guys know this. And that's going to be
friction coefficient multiplied by the normal force.
Very well. So Ft, in order to mobilize this solid, the bigger the force, the normal force, the bigger Ft, and Ft will be equal to the friction coefficient times the normal force. So again, the bigger the normal force, the bigger Ft required to make that solid move. All right, so I was working on this example to show this in class, but with a granular material, but I'll show that on Friday. But the idea is that it's exactly the same with rocks. Let's start, just to make it simpler, with an uncemented rock. An uncemented rock is just a bunch of grains. All right, the idea here is that if you have effective stresses on the side, sometimes I like to call it also these skeletal stresses, because they are applied on the skeleton of the rock, which is the solid part. If you have an effective stress applied on this granular solid, let me make a zoom out of here. The idea is that in the contacts between grain and grain, the bigger the effective normal stress grain to grain, also the harder is going to make, is going to be in order to move these surfaces one relative to each other. So it is exactly the same idea as here, where this is a grain surface and this is another grain surface. So the more effective normal stress I have applied on this, the more difficult it's going to be for these grains to move relative to each other, because you have a friction force between the grains. And that frictional force or frictional stress, similarly to what we had before, is going to be the friction coefficient times the normal stress. But now this is going to be in terms of stresses, not in terms of forces. So what we're going to see then, and we're going to prove here in class, is that similarly to a block of a solid displacing on a flat surface, for rocks, and in this case for unsymmetric rocks, the bigger the effective normal stress on a particular granular material, the bigger is going to be the stress required for that rock to fail or to form a fracture. So before, and this is a key thing that I have to say. This will, if I were to start increasing Ft, let's say Ft is 0, Fn is a value and Ft is 0. Then I keep increasing. Here there is no slip. But when I get to that point, that is when I get the block to slip respect to that other surface. Similar to this case, what this line is showing is the maximum shear stress that the material can hold before it fails. And the equation, as we said, is going to be this. Okay. So if I have an example, you will see this will make a lot of sense, a lot more sense than it might do right now. But I couldn't make it work and I forgot something else. But we'll see that on Friday. On Friday, what I'm going to show is that we can have a non-consolidated granular material at a given pressure or a given confining. We'll do this with atmospheric pressure. If I apply an atmospheric pressure or confining stress on a solid, I'm going to be able to load it in perpendicular direction with so this one is going to be atmospheric pressure on the sides. If I manage to do that, I'm going to be able to load it with a bigger stress in perpendicular direction that will be delimited by this shear line, and this is going to be the axial stress at failure or at shear yield. What is what I just drew, guys? You remember what this is? What is that circle? It's a Mohr circle. And if you remember, what the Mohr circle does is it represents state of stresses at different angles. For this particular case, the state of stress is given by the stress in this direction and the stress in perpendicular direction, sigma A, where these two stresses are principal stresses. You remember the discussion that we had about principal stresses? We said that a principal stress is a principal stress whenever there are no shear stresses applied on that plane. And this is the case. There are no shear stresses applied on either this surface or the top and the bottom. And therefore, those are principal stresses. And in this type of plot, they will plot as 2 points on the x-axis, which is the axis of normal stresses. All right. So principal stresses, normal stress is different than 0. and shear stress is equal to 0. So we're here. So let's see now what this circle is and how it links to that line. Okay, the circle tells you what is the, let me see, I don't remember if I explained this here or later. No, I think I do it here. Okay. Let me add one more thing. In this particular case, this is going to be the minimum principal effective stress, and this is going to be the maximum effective stress. The intermediate stress sigma 2 is equal to sigma 3, so I'm not going to write it. Okay, so I can redraw this plot, and let me not draw the grains just to make it simpler and to see what's going on inside. I have stress sigma 1 on the top, same on the bottom. These lines supposed to be the same length. And I have a stress which is smaller in perpendicular direction. So this point corresponds to this top face. This point over here, let me add it with dashed line so it's clearer, corresponds to, let me pick this surface over here. So sigma 3, sigma 1. All right, now we go with the circle. The circle is going to mean all the state of stresses from a given plane at an angle, let's call it beta. Where notice, when you go from the face of sigma 1 to the face of sigma 3, the change of beta is 90 degrees. But in the Mohr circle, when you go to this point to that point, the change is 180 degrees. So in the Mohr circle, the change of the angle is going to be 2 times the actual angle. So in the Mohr circle, if I want to draw this angle beta, I'm going to go from the center, and this is going to be 2 beta. And at any plane, what I try to solve with the Mohr circle is what is the normal stress perpendicular to that plane, and what is the shear stress perpendicular parallel to that plane. And these two values are just a point in this 2D plot, sigma n and tau. So if I know what is a given angle, I can get to know what is the value of the normal and the shear stress. And let me see. What we want to try to solve here is what is going to be this value at failure, or how many times sigma 1 is going to be as a function of the friction angle, how many times sigma 3, how many times sigma 1 is going to be sigma 3. So basically what I want to answer is what is the value of sigma 1 as the value of sigma 3 and the friction angle. And that's going to depend on this line. So if I were to load this rock, and I would start with the isotropic state of stress, that would be just a point. And how big the angle this circle gets depends on this line. this line is going to limit the maximum normal and shear stress, which is going to be that point. If I had a bigger friction angle, for example, a line over here, my circle will get bigger, and my value of sigma 1 will be bigger. All right? So let me solve this problem of, I want to know how many times sigma 1 is going to be with respect to sigma 3 at failure. And in order to do that, we're going to use the shear failure line. All right, so notice that we have a circle here, where this is the center of the circle, and this is the radius of the circle. So sigma 1 divided sigma 3 is going to be, sigma 1 is the center plus the radius, that point over there, and sigma 3 is the center minus the radius. Okay? What is the radius in terms of the center? I'm going to add one more definition here. Here we have the friction coefficient. But also in geomechanics, we like to work with the friction angle. What is going to be the sign of the friction angle? In this particular case. Can you see that on the figure? Sign of friction angle. This is in this particular example, at the maximum point, this is going to be a right angle, and this is just R divided by C. So R is the opposite side, and C is the long side of the triangle. So this is just going to be R divided by C. And therefore, R is going to be C times sine of the friction angle, and all the C's are going to cancel out, and the result is going to be that sigma 1 divided sigma 3 is going to be 1 plus sine of phi, 1 minus sine of phi, and this is what is called stress anisotropy, where phi is angle, and a typical friction angle is about 30 degrees. So for phi equal to 30 degrees, what is going to be the maximum stress anisotropy of an uncemented material? Sine of 30 is 0.5, very well. So 1.5 divided 0.5, it will be equal to 3. And you remember that I told you to remember the number 1/3, because 1/3 will be important later on. Remember that with elasticity and with the Poisson ratio of 0.25, we said that the effective horizontal stress will be 1/3 of the effective vertical stress with no tectonic strains. Well, in this case, what this equation is telling me is that the maximum effective stress is going to be 3 times the minimum effective stress, or the same, that the minimum effective stress is the maximum effective stress divided by 3. So with totally different theory, we're arriving to similar conclusions that we did before. We'll see how we use this later on, okay? But for now, what I want you to remember is that when you subject a solid to compression, and even if it's not cemented, it can resist a stress which is higher in one direction as long as you have another stress in perpendicular direction. And the maximum value is going to depend on the friction angle. And for a typical friction angle, the maximum stress you can put on vertical direction, if you're applying a vertical loading, is going to be just 3 times the horizontal stress. And why? Because otherwise, the rock is going to fail in shear. And when it does fail in shear, what we will get is a failure plane, which is going to be, let me do it with color, is going to be a steep plane. Another thing that I wanted to answer today, what is going to be that angle? Notice that when a rock fails is when the circle touches that line. And that's when the circle is tangent to that line. If this is a friction angle, and this is a friction angle too, because this is a horizontal line, what is the angle I need in order to get to that maximum point? I'll give extra points whoever tells me the answer. Don't cheat, okay? Don't look at the solution in the notes. So basically, what you have to do is you have to go an angle which will be equal to getting into that line, where that line is a right angle. Let me give you a hint. Because of the properties of lines and triangles, this angle over here also is going to be phi. So this angle is that one. Therefore, 2 beta is going to be equal to what? Two beta will be equal to 90 plus that thing, which is a friction angle, and therefore beta will be equal to 45 plus friction angle divided by 2. And that is that angle. If you remember from the test that we did in class, and I have here another rock, this is what you actually see when you fail a rock in shear. You see a steep angle, which is, and when I mean steep, is that it's higher than 45. So I think I have drawn some of that, some of these rocks. Okay. Yeah. Something like this. So the angle, either from the, this is not this side. I think it was something like this. Okay, let me find it right. Okay, this was the one. We could either measure the angle from this plane into that one, or here to that one is the same, but that angle is going to be always a steep angle when I measure it from this plane. And here you have the equation. It tells you that it has to be 45 plus friction angle divided by 2. And for a typical friction angle, what is going to be the angle at failure? 60 degrees. And you see that more or less this angle over here, it's 60, 60 something. This is something very important that I want you to remember because we're going to apply it a lot later on. What is the angle with respect to the maximum stress? All right, guys, I'll see you on Friday. Remember that I want you to attend because we're going to do this laboratory test.